Adelaide's initial toss gives the ball kinetic energy, or the energy of motion. The kinetic energy of the ball depends on its mass and speed, which comes out to 0.4 joules. The average mass of a tennis ball is 0.056 kilograms, and we obtained our vertical distance by measuring the average height of her toss and the time by rewatching the video. At the peak of the toss, the ball's kinetic energy momentarily shifts to potential energy because of its position. Its potential energy is based on the ball's weight or its mass times Earth's gravity multiplied by the height, resulting in 1.6 joules. Again, 0.056 kilograms is the average mass of the ball, while 9.8 meters per second squared is the acceleration due to gravity, and the height was Adelaide's average toss. As it falls, its potential energy is converted back to kinetic energy as Adelaide prepares to hit the ball.
The kinetic chain begins with the motion of Adelaide loading up or preparing to hit the ball by bending her knees. As Adelaide begins to stand, her kinetic energy is transferred to the abdomen and her core. The energy continues to work its way up the kinetic chain as Adelaide cocks her arm back. The energy is delivered to the arm and ultimately through the wrist onto the racket. Once the racket collides with the ball, all the energy that has been built up is imparted on the ball.
Adelaide's swing results in an elastic collision as the momentum of her racket transfers to the tennis ball. The two objects momentarily come together before they separate, causing the ball to move forward. This is an example of an elastic collision, as the ball and racket come together before accelerating apart. Also, this collision follows the law of conservation of momentum, with the net momentum of both objects before the collision equaling the net momentum of both objects after the collision.
The racket provides the force necessary for the tennis ball to accelerate. We assume that the ball traveled diagonally straight down, so all our calculations will be derived from that. Acceleration is calculated by dividing the net force in the mass, and the ball's acceleration is 70 meters per second squared. The length was figured by approximating the distance the ball traveled, and the time was obtained by rewatching the video.
As the ball makes contact with the ground, it demonstrates Newton's third law of motion, which states, for every action there will be an equal and opposite reaction. When the ball hits the ground, it imparts all of its kinetic energy into the ground, which then pushes back with an equal force, causing the ball to bounce. The force that the ground exerts on the ball, and vice versa, is 3.8 newtons. We calculated acceleration by using final velocity equals initial velocity, plus acceleration times time. Our initial velocity was 0, and our final velocity is 20.6 meters per second. 0.3 seconds was the time it took for the ball to touch the ground once it was hit. With all our values in place, we simply solved the equation for A, which came out to 68.7 meters per second squared, and multiplied that by the average mass of a tennis ball.
Do you need tennis shoes?
Yeah.
Oh! Oh! That was it. Okay. Oh shoot, don't get that. Wait, let me drop that.
Where did the ball?
It's not hard.
No, I know, but like we'll need to show a video.
Yeah.
Oh!
Hey!
But it works.
Are you ready?